This is our second video of our heat load calculation series. So part 2, we're going to talk about the methods of heat transfer. Now, why this is important is because when you have heat leaving or entering a home or any other building, it comes in three ways. And you have to understand these three ways so A, you can compensate for it with your sizing of equipment, and B, so maybe you can prevent some of this heat transfer from going on. So our three methods of heat transfer are conduction, convection, and radiation. We're going to talk about conduction first. Okay, conduction is a heat transferring that's occurring through solid materials. Okay, from experience, we know if we touch the sides of the pan with boiling water, we'll be burned. Okay, why do we know that? Isn't the flame only on the bottom of the pot? So one of the questions we have to ask is, how does the heat get to the sides? Okay, what happens is the heat is conducting through the material. Okay, you heat the bottom of the pot, the heat goes all the way up the sides because metal is a great conductor of material. So conduction transfers energy or heat, because heat is energy, through matter from particle to particle. Thermal conductivity, or the letter K, small k, is a measurement of how well heat transfers through material. For example, does heat transfer through glass in the same manner it transfers through copper? Or does heat transfer through fiberglass in the same manner it transfers through copper? Or, when you're talking about a home, what color material does heat transfer the best through? So this is all having to do with thermal conductivity. The higher the conductivity, the faster the heat transfers. Conduction is inversely proportional to the thickness of the material. Okay, the thicker the material, the lower the rate of conduction. Double the thickness of material while maintaining the temperature difference between its side, the rate of heat transfer through the material is cut in half. The temperature difference is important because the larger the temperature difference, the larger the heat transfer. So if you have a 70-degree inside environment and a 0-degree outdoor environment and a material half-inch thick, if you change that to an inch-thick material with keeping the temperatures the same, you cut the heat transfer in half. In buildings, conduction occurs easily through building materials such as the metal, the glass, and the concrete. Poor conducting materials are usually used as insulating materials. For example, fiberglass, insulating foams, and mineral wool. Now, all of these have one thing in common. They have a lot of air space in them because, believe it or not, air is a really great insulating material. The ability of material to conduct heat is a measured by a property called thermal conductivity. Okay, dividing this value by the thickness of the material, which would be L in this formula, measured in inches, yields a very important term called the coefficient of heat transfer, or the U factor. We're going to use the U factor as we move on. So again, you take your thermal conductivity, you divide it by the thickness measured in inches, and you get your U factor. And that is a very important formula to know. So U equals K divided by L. So the normal sequence when solving a conduction problem, look up the R values for the materials in a building cross-section. Those you can find from catalogs, books, everything. Add those values and then take the reciprocal of that answer to get the U factor. Reciprocal, just take the R value and divide it into 1. So 1 over R equals U. Conduction can happen very well in fluids as well as solids. Okay, they only feel colder because they conduct heat away from your hand to another object colder than your hand. Again, heat is going to move from hot to cold. Your hand's hot, we take a cooler liquid, it's going to conduct heat away from your hand. So metals tend to feel cold, but they may not always be cold. Our next form of heat transfer is convection. Okay, ASHRAE has a definition of thermal convection. It's the heat transfer by movement of fluid, or for heat to be considered convection, fluid in contact with the surface must be in motion. If not, the mode of heat transfer is conduction. So again, moving fluid. Okay, we also take moving air as convection. Convection heat transfer occurs when fluids at different temperatures move around within a space. So this pot of boiling water, okay, the pot itself is conduction because that's non-moving metal. It's a solid. Now the water in there transferring heat to perhaps the egg that you have boiling in it, or there's something boiling in it, that would be convection because the water is actually moving in this pot as it boils. Convection is the transfer heat energy in a gas or liquid by movement of the currents. The heat moves with the fluid. Okay, and again, we throw gas in here, but that could be air because air is a form of gas or a mixture of gases. Convection heat transfer occurs when fluids at different temperatures move around within the space. There's two types of convection. So we have free and forced. Free is natural convection. We all know heat rises because the molecules are more active and they're going to rise. Forced would be taking the blower motor or pump in our furnace or boiler and forcing fluid or air to move around. So for free natural convection, it uses the natural buoyancy of the fluid to drive the convective flow. In the winter time, heavy air falls down windows, creating drafts. Hot or lighter air rises as it counters it, okay? So the cold air is heavy, it falls. Hot air will rise to the ceiling, so you'll start getting draft patterns. Now, forced or mechanical convection is most of what we use now in modern day furnaces and boilers. We use a fan or pump to force the flow of the heated fluid. Okay, so a ceiling fan is an example of forced convection. Hot air rises and then is counteracted by the fan pushing the warmer air back down into the living zone. That's why you'll see a lot of ceiling fans in a lot of commercial buildings with big entranceways. Warm, rising air thermals due to heat rising from the earth. As the warm air rises, cool air comes in from the sides to take its place. This setup is a circulating flow of air. Convective heat transfer occurs when fluids at different temperatures move around within the space. So this is an example of natural convection. Okay, it uses the natural buoyancy of the fluid or gas to drive the convective flow. Hot air rises. Take a look at the chimneys and the steam releasing in the picture. Hot air on a cold day is going to rise. Forced convection depends on a pump or fan to force the flow of heated fluid or gas. Okay, and we've already talked about free or natural convection. Okay, forced convection depends on the fan or pump. Now, radiation is the final form of heat transfer we have to talk about. Okay, radiation is electromagnetic energy. Okay, it does not need material to transfer heat from one location to another, and it travels outward from its source in straight lines at the speed of light. It cannot bend around corners, but it can be reflected. So a surface emits thermal radiation to any cool surface within sight of it. Okay, so if I have a hot piece of metal or a hot ball, it's going to emit thermal radiation to any cooler surface within direct line of sight. That's a straight line. So, of the three methods of heat transfer, how does solar energy get to the Earth? It's radiation. Okay, couple things to talk about, couple thoughts in this exercise section. Okay, identify the method of heat transfer. Okay, this would be conduction. You have a solid object. What's the method of heat transfer? Okay. It's still conduction. We have solid objects. What's the method of heat transfer? The ball in the sunlight. That's radiation. Method of heat transfer here. Could be radiation from the light coming off the fire, but it also could be convection going because the air is moving around that fire. Method of heat transfer here, we have two. Conduction and convection. We also have a third. We could also have radiation because the grate to the metal holder, pot to the metal holder, pot to stovetop could be radiation as well. Okay, a couple other things. Brownies bake in a glass pan using these two methods. Okay, conduction and convection. Or convection and radiation, depending on the oven you're using. Heat in a room moves with the warm currents from a warmer areas to cooler areas. Convection. Air currents. You feel the heat of a wood stove when you stand next to it. We have convection and radiation. Warm air rises in a lake, cold water descends. Again, currents. Convection. A thermometer you have under your tongue shows you have a high fever. What type of heat transfer? It's conduction. Solid objects. The sun transfers its heat to our planet through space. What type of heat transfer? Radiation. On a cloudless night, the heat escapes from our planet and goes into space. What type of heat transfer? It's radiation. You place a spoon in a cup of cocoa and it gets hot over time. What type of heat transfer? Conduction. Blank is measured with a thermometer. You have a choice of A, B, or C. Heat, or temperature, or radiation. Well, you can't really measure heat. Okay, that's a form of energy. So you can measure temperature. A thermos bottle has a shiny interior. What type of heat transfer does it prevent? Radiation. So that's where we're going to leave off part 2 of this series. Okay, we've now talked about the 3 types of heat transfers. We have the conduction, we have the convection, and we have the radiation. Conduction is solid objects, heat movement through contact with solid object. Convection is having to do with currents, or fluid or air. Radiation, straight line of sight.